All right, this is Senior Design 2 project overview for ChessBot Team 20.
Okay, so the project goals for this project are to create a chess bot that is under $350. It plays chess against a live player. It'll detect the board state using computer vision, which we're using OpenCV for. It'll determine the move after the computer vision sees the board state using Stockfish, which is a well-known chess engine, and then it'll move the pieces using a robot arm. So the block diagram for this kind of shows how the flowchart of like which section does what. So first, the user will make a move, which will impact the board state, obviously. Then the camera will read the board state and it'll pass it to OpenCV, which will determine what change occurred. The change will then show on the display and we'll pass that change to Stockfish, which will output a move, and the move will go to the ARM controller, which is also code, and then that tells the robot arm where to move. The robot arm will then make a move, and then obviously change the board state, and then we're going to be wait on the next user move.
So the chessboard we're using is 8.5 by 8.5 inches with a metallic arm with 5 degrees of freedom and a 5 kilogram electromagnet at the end. We're going to have a monitor that is serving as an HMI that connects the user to the robot. And it will allow the user to know what moves have been taken and keep all that information displayed. The servos we're using 5 servos, and they are pretty heavy duty, 35 kilogram servos, and those are used to move the arms. And then we are using a servo driver to control them instead of going with the Raspberry Pi. And then for the electromagnet, we're using an H-bridge motor driver to power it in both directions. ARM and base design. We actually had a sort of a constraint on the board itself. We had to downsize our board originally because the original was so big, and we realized that we didn't have a big enough motor arm to actually hit all the squares. And so this board, you see, our arm is barely large enough to do it. Those 2 buttons you see on the left and right side, those are going to be, the left one is our start button, and the right one is our stop button, essentially. And then behind all that is the actual circuitry that's covered up by a box on which a monitor sits, which actually displays the HMI, giving the user all that feedback.
So this is a flowchart detailing our software structure. Essentially, the camera takes an image of the board, which is then sent to OpenCV, our computer vision program, to determine which pieces are on which squares. This is put into an 8x8 matrix representing the board and is sent to our UCI translation program. The UCI translation program determines which moves are made and sends them to Stockfish to determine whether the move is valid. If the move is not valid, the display tells the user to try again. If the move is valid, then Stockfish will return a move of its own, which will then be executed by the robot arm.
The way that we originally did the ARP control was with a big lookup table, so that we mapped all 8x8 squares to a specific angle value with the given 5 motors. So all 5 motors are going to have some angle, essentially a pulse width modulated signal, but it's an angle on a lookup table, and we say, hey, go to A5. The code says, okay, I'm going to use that A5, and I'm going to use it to determine and pull out the 5 motor angles, and I'm going to send those to my chip. And we did this because in order to go and do reverse kinematics, the first thing I had to do was get a good sense of how the robot moves in space so that I understood sort of design constraints. And by the end of the design process, I had math and equations that worked decently well. It wasn't ready to be plugged in or anything. But we definitely wanted to do reverse kinematics because we realized the amount of time and effort it required to map one-to-one with all of the motors in all of the different ways took a tremendous amount of time. We just ran out of time to really implement reverse kinematics, which we wrote. And reverse kinematics would be where you give a robot the end coordinates you would like. Hey, I want you to go to point X, Y, Z in space. And then it uses a whole bunch of math and trigonometry to determine what angles are required for your motors to achieve that given place.
All right, and for the electromagnet on the arm, we control through a motor driver, an H-bridge motor driver to be specific, because we wanted to be able to have bidirectional current to this electromagnet, as it would push off the pieces from the magnet and pick it up. This ended up being unnecessary just because when building the final model, modifications were made to the electromagnet section that allowed for the pieces to fall off just by turning off the electromagnet. So really, we could just hook it up to a power supply and turn it on and off.
So this video, the computer vision, shows a demo of how it works. So as you can see, I'm going to move the pieces around, and you see the updates on the board. The reason why the video looks so choppy is because we added in a delay to prevent the Pi from trying to do too much work at a time, because it's trying to run the computer vision, the GUI, and also Stockfish in the background. So how it works is, first it takes in the entire image, and then it filters by color. So there's 6 different colors for each of the different pieces, and then it only filters by color in the area that we care about, which is the game board, and it ignores everything else. After it filters by color, it does a couple of morphological operations to remove noise, essentially, and then it looks for circles. To find a circle, it takes all the shapes it finds and then looks for edges and then contours. And for each circle contour that it finds, if there's a black center, it'll label it as a black piece, and if there's not a black center, it's a white piece. Each square on the chessboard has a center value, and then there's a radius associated with it, and if the circle is either inside of it or touching it, it's considered on that square. So the radius is just big enough so there should only be one piece on a square.
The UCI translation program that we described earlier can be broken down into a few parts. First, it will receive an 8x8 matrix from computer vision, which represents each square on the board. Then the UCI translation will determine the move made by the player by comparing the current board state, which was just sent, to the previous board state, which was saved. Then the move will be sent to Stockfish to determine whether it was legal or not. If it was illegal, the display will tell the user to make another move. If it was legal, then Stockfish will compute a move of its own, which will then be sent to the ARM control and executed by the ARM. We did run into some challenges and bottlenecks. ARM control is very difficult to implement in general, but especially implementing it with the required precision and not knock over other chess pieces made it take a very long time. Computer vision also took extensive tuning in order to be accurate enough to consistently identify pieces and not cause errors with Stockfish. We also had a few bugs show up whenever we integrated all of our programs together with the hardware.
Okay, so the first part of the demo is an example of the GUI working, which first you see the initial state of the chessboard. So we can basically start by getting the current board and then forcing the game to start from this position, which the set game board button does. And then I display the Stockfish to show what the Stockfish engine sees, which is correct. Then I'm going to go ahead and make a move for white. You can see the changes reflected on the current version, and then I'm going to hit get current board, which will update it, and then validate the player move to make sure that it's correct. And then it got accepted, and then I'll get the Stockfish move, which is B7, B5.
The video that we're about to watch is of the arm moving, and so where it starts out is what we're going to call our origin location, and it has to be off of the board, and it needs to be off the board so that the camera above can actually capture the board state. The very first move we do is we go to a center location that we've predefined so it's really high and it's not going to knock any pieces over. From there, the computer vision is going to give the Pi basically hey, I want you to go to some specific location, and then that location maps on to servo values, and so you watch it initially go to a value that's close and then lock in on, in this case, it's B7, and so now all the values are right. Electromagnet's going to turn on. It's going to return to the center location, and then it goes back low to the new location, drops the piece, and then after that it should go all the way to the very top. So first it has to swing all the way over, then it's going to drop and essentially park itself back down.
So in the next video, we see the updated game board after the movement happens. So we're just going to get the update and then use the set game board button and then display Stockfish and show that the game board has in fact been updated from the previous position.
We concluded that our arm movement is slightly imprecise due to servo movements and the arm and base construction not being as sturdy as we would like it to be. Computer vision can very reliably read the board state. UCI translation can turn this input from computer vision into UCI that is readable by Stockfish. Stockfish is able to return moves based on the board state after validating them to make sure that they are legal, and it is able to play chess against a player in most cases.
For further work, we do need to add a clock and physical switch for the robot to be timed. There was plans to make that happen. However, with time constraints, we couldn't quite get the code to work. But we do have it wired up. We just need to get the code right. We need to add more LEDs. I was planning on adding an LED for the electromagnet to indicate whether it was pulling or pushing or off. We also need an LED for each servo to indicate which servo is moving at the current time. We need to add difficulty settings based on ELO depth and thinking time. And then we need to implement reverse kinematics, ideally, so that we don't have to enter 960 angle values.